What's up, class? Trent here,
Tyler here.
and we're here to tell you about Chapter 9 of the AP Stats book, which deals a lot with the null hypothesis, alternative hypothesis, type 1, type 2 errors, and then finding the test statistic and really interpreting that into a p-value and really defining what that means.
So before we begin our lesson for the day, let's describe what a null hypothesis, alternative hypothesis, type 1 error, and type 2 error is. The null hypothesis is what is assumed to be true before an experiment, i.e. the default position. What's important to note with the null hypothesis is that it can never be proven correct. Through experimentation, we can only reject or fail to reject. For example, if we compared two groups, one that was treated with medication and one that was not, and our experiment reveals no statistically significant difference between the two, it does not prove that there is really no difference. It only shows that there was not enough data to reject the claim that the medicine helped.
For the alternative hypothesis, or technically the rival of the null hypothesis, it proposes a different answer than the null. However, like the null hypothesis, we cannot mathematically show that the alternative is true. Rather, we can reject the null in favor of the alternative, or we can simply fail to reject the null.
Now, a type 1 error is the incorrect rejection of a true null hypothesis. That is to say, we rejected the null hypothesis, however, the null was actually correct and we mistakenly rejected it. Conversely, a type 2 error is the failure to reject a false null hypothesis. That is when the null hypothesis was incorrect, but we were unable to reject it at that significance level.
Now, you might be wondering, how do you know how likely you are to make a type 1 or type 2 error? Because that could be a big deal depending on what the situation may be. So the probability of making a type 1 error is equal to the significance level, and that would normally be given to you at the beginning of a problem, but if not, you can likely assume that is equal to 5%. On the other hand, a type 2 error is equal to beta.
Now, beta can be found using the equation power equals 1 minus beta. Now, the power can be found of a statistical test. Sorry. That will reject. The power of a statistical test is the probability that the test will reject the null hypothesis when the null hypothesis is false at that significance level.
Now, it's time to put this all together. And to do that, we've really defined our variables. Now we just have to use it to put into a test statistic. And the equation for a test statistic is equal to the statistic minus a parameter divided by the standard deviation of the statistic, which would look like this. Or you're finding z, which is equal to p hat minus p null divided by the square root of p null divided by p null times 1 minus p divided by n. And that will give you the z-score.
So, for our practice problem, a basketball player claims that he makes 80% of his free throws. So, we don't really believe this. So, we conduct an experiment to either reject his claim or not reject his claim. Not necessarily prove it's true, but just not reject it. So, we do a simple random sample of 53 free throws, and the player made 32. Now, calculate that using that statistics, calculate the p-value, and say if you can reject his claim of an 80% success rate at a 5% significance level.
Now, we're going to just walk you through the problem because it's your first time, but next time you guys will get it. So first things first, you want to define your variables, just to make things more easy to go through the problem and know where each number is coming from. So you probably want to set n equal to 50, which is the number of free throw shots he took. Then the significance level is equal to 0.05, because that was given to us at the beginning of the problem. P hat is equal to 0.64, and you find P hat dividing 32 divided by 50, or the free throws he made divided by the number of free throws he took. And then through these, we can claim that the null hypothesis is P equals 0.8, or the parameter is that he makes 80% of his free throws, because he claims to be an 80% free throw shooter. Alternatively, the alternative hypothesis would be P is less than or equal to 0.8, because we believe that he probably makes less than 80% of his free throws.
Hold on just a second, Trent. Before we conduct this test, we have to make sure that we can actually use this equation in order to test it. So we have to make sure that a few parameters are met. First, we have to make sure this test is independent. That is, each of his shots were independent of the other and didn't have an effect on each other, and in this case, that's true. Second, we need to make sure that it is random. which it says it's random, so it's random. And finally, we need to make sure it's a normal curve, which is we can use the equation given by Trent earlier to make sure that it is greater or equal to a total of 10.
And just to review what that equation is for normal, it would be n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. And in our case, n would be 50, p would be 0.64, so that's equal to 32. On the other hand, if you take the reverse of p, and then you do that math, it's 18. So, moving on from there, we want to plug all these values into our equation to find the test statistic. So, if we do that, we get 0.64 minus 0.80 on the top divided by 0.0566, which is the standard deviation of the test statistic, which would be calculated by doing the square root of p null times 1 minus p null divided by n. And if you do that math, you should get negative 2.83. And negative 2.83 is z. And you can then plug that in and show that on a normal distribution curve or a normal distribution graph just to make it a little bit easier to see really what you're going for, like we have done here. And as you can see, you have a normal distribution curve with 0 as the mean, and then you plot your negative 2.83, and you can see that you want to find everything to the left of that, which will tell you your p-value, which is a probability that he will shoot 64% if he actually is an 80% free throw shooter.
So now, after plugging in on this equation, we found that the probability of that occurring is 0.0023, which is basically a 2 in 1,000 chance that if his claim of 80% success was true, that he would shoot this, it's pretty low, so he's a liar.
And there's really two main ways you can find this p-value, even though there's a bunch of other different ways on the calculator, but my preferred way is using normal CDF, negative 10, which is your lower bound, negative 2.83, which would be upper bound because you're finding up to that negative 2.83 or z value we found, and then 0 for the mean and 1 for the standard deviation. Also, you could simply look in the back of the book and compare the test statistics. And also, when you're doing this, and when you're trying to find the p-value, you want to make sure you write it in the correct format to get that 5 on the AP stat test. So that'd be p, then parenthesis z is less than or equal to negative 2.83. That's just like technical stuff, but that's how you should write it. And then again, you'd get 0.0023 as your answer.
Nice. So done?
Not right. So at that significance level, we get a p-value of 0.0023, and we had a significance level of 0.05, which means our p-value is less than our significance level, which means we are going to reject our null hypothesis. So we would say something like, at a significance level of 0.05, we will reject the null hypothesis that he is an 80% free throw shooter in favor of the alternative hypothesis that he is less than 80% free throw shooter.
Note the key language here. We don't actually say that he will shoot less than 80% of free throws. We simply say that our experiment suggests that his claim is false. So we're not actually proving any alternative hypothesis here. We're simply suggesting that the null hypothesis should be rejected in favor of a different hypothesis.
It's been a blast, class. Shout out to Will Beard. Can't wait to watch this in class.